Hello, welcome back to my channel. Today we are going to discuss Chapter A, Rotational of Rigid Body. So in this video, we are going to learn torque. When a rigid body is subject to the net torque, where torque is not equal to 0, it undergoes an angular acceleration. The angular acceleration is directly proportional to the net torque. Okay, where the relationship is actually analog to the Newton's second law, where F equals to ma. So for rotational, our equation is equals to net torque equals to I alpha. The angular acceleration is directly proportional to the net torque, and the angular acceleration is inversely proportional to the moment inertia of the object. Okay, so next we will go to exercise number 6. Here we have two forces, F1 and also F2, and apply tangentially to the disc with the radius of 30 cm or 0.3 meter, and the mass is 5 kg. So first one, find the net torque on the disc. Here we have two forces, meaning that our net torque is equal to torque 1 and also torque 2. Okay, where we know that torque equals to Rf sine theta. Okay, so here F1 here, radius is from the center, radius, and F here is 90 degree. So we can write torque 1 is R F1 sine 90 degree. Radius is going up and F1 is going to the left, meaning that it's actually anti-clockwise. So when we say anti-clockwise, torque is positive. F2, from the center, the radius is R and the force is acting upward. Here, if you refer from the radius to the force, it's actually clockwise. Okay, so when we say clockwise, it is negative. Okay, so we write negative R F2, and the angle between them is 90 degrees, so it's sine 90 degree. Okay, so we substitute in positive R is 0.3, F1 is 5.6, sine 90 is equal to 1. Okay, minus R 0.3, F2 is 10.3, and again sine 90 is equal to 1. So therefore, the net torque is negative 1.41, unit is Newton meter. Okay, so negative here shows that at the end, this disc will rotate in clockwise. Okay, next one, B. Find the magnitude of the angular acceleration, meaning we want to find alpha. So we know that net torque equals to I alpha. Okay, where our net torque is negative 1.41, and I here is given 1 over 2, m is 5 kg, r is 0.3 square, and then alpha. Okay, so therefore alpha we will get negative 6.27 radian per second square. Okay, but the question asks us to find the magnitude only. So therefore, the magnitude of alpha is equal to 6.27 radian per second square. Questions number 2. An object of mass 1.5 kg is suspended from a rough pulley. So here there is a mass of the object 1.5 and the radius is 20 cm, but the light string. The pulley has the moment inertia. Okay, so this is the pulley and the moment inertia is 0.02. The object is released from rest. So initially it's at rest and the pulley rotates without encountering frictional force. So we can ignore the frictional force of the pulley. Okay, assumes that the string does not slip on to the pulley. So after 0.3 seconds, determine the linear acceleration, meaning that we want to find A. So for this question, actually it applies Newton's second law. Pulley is rotating. Okay, so it experiences a net torque where our net torque equals to I alpha. And at the same time, this object 1.5 kg, it experiences a F net is going downward. So F net equals to MA. Okay, so if you refer back to the pulley, this pulley is rotating downward. Okay, here is tension. Okay, so and the radius is r. Okay, so our net force is equals to r, and the force here is tension equals to I alpha. R T tension, I alpha, we can change it into A over R. So therefore, tension is equals to I A R squared. This is our first equation. Okay, the second equation is from this 1.5 kg object, where this object, it will experience two forces. The first one is tension, the second one is the weight, and the motion is going downward. Okay, so when the motion is going downward, meaning that is mg minus tension equals to ma. Okay, so our tension will equals to mg minus ma. Okay, so this is the second equation. So we substitute equation 1 into equation 2. Ia over r squared plus ma equals to mg. So we factorize out a, we will get I over r squared plus m equals to mg. Okay, so therefore a is equals to mg, m is 1.5, g is 9.81 over I. So I is the moment inertia, 0.02 over r. R is 20 cm, so it's 0.2 square plus m. M is 1.5. Okay, so finally we will have a linear acceleration equals to 7.36 meter per second square. Okay, B. So we know that alpha equals to A over R. So after we get the linear acceleration 7.36, so we divide by the radius 0.2. So therefore, angular acceleration is equals to 36.8 radian per second square. C. Find the tension. Okay, so tension from equation 1 is equals to Ia over r squared. Okay, where I is equals to 0.02. A is the linear acceleration 7.36, and r is the radius 0.2 square. So finally we will get tension equals to 3.68 Newton. Okay, next one, find the linear velocity v. Okay, so linear velocity v, we must find out first what are the informations that we have. Here the question says release from rest, so meaning that u is equals to 0. And we also have the acceleration, linear acceleration, a equals to 7.36, and t is given 0.3. So we can find our linear velocity. So v equals to u plus at. Substitute into the equation, u0 plus a is negative because it's acting downward, the motion is downward. So a is negative 7.36 times 0.3. So our velocity is equals to negative 2.21 meter per second. So negative here shows that the directions of the linear velocity is acting downward. Okay, next one, E. The distance traveled by the object. So S equals to ut plus half at square, where u equals to 0 plus half, a is negative 7.36, t is 0.3 square. So finally, the distance traveled, we will get negative 0.331 meter. Again, negative here shows that the displacement, the object is moving downward. Questions number 3. A solid cylinder of the radius 18 cm is free to rotate about a smooth horizontal axis. A mass of 0.38 kg hangs from the string. So here there is a object 0.38 kg. Okay, is hang from the string. So when the system releases from the rest, meaning that initially u is equals to 0, the mass takes 2 seconds. So t is equals to 2 seconds to fall through a height of 5 meter. So the s is equals to negative 5 meter because it's acting downward. So what is the moment inertia of the cylinder? We want to find I. Okay, so for this case, similar like questions number 2, this cylinder is experiencing a net torque. Okay, it's rotating, and this object is moving downward. Okay, so we use Newton's second law, where the first one for rotating is our net torque equals to I alpha. And the second equation is F net equals to MA. So this is for linear motion. For the cylinders, this cylinder, there is a radius and it experience a tension T. So our torque here is equals to radius times the tension, okay, sine 90 degree equals to I alpha. Okay, where we have we can write as tension equals to I alpha over R. So this is our first equation. Okay, for the second one, linear motion object. This object is experience a tension and also mg. And because the object is falling downward, so the motion is acting downward. So therefore our net force is equals to mg minus tension equals to ma. So this is our second equation. Okay, so our equation 1 equals to equation 2, where our tension here is equals to I alpha over R equals to mg minus ma. Okay, so if you want to find I will equals to mg minus ma times R over alpha. Mass of the object is 0.38 times 9.81 minus 0.38 times A, where A we don't know, and then R is given 0.18. Alpha, we know that alpha is equals to A over R, so we can change alpha become A over R. A over R here will become R squared. So we must find A first, the linear accelerations, before we can find the moment inertia. So here we have U, T and S. We want to find A, meaning that we can use the linear motions to find S equals to ut plus half at squared, where S is equals to -5, U is equals to 0 plus half, A is the value that we want to find, and T squared, so it's 2 squared. Accelerations is equals to -2.5 meter per second squared. So if we substitute into the equation 0.38 and then we factorize 9.81 minus, okay, we only take the magnitude only, okay, take the magnitude 2.5 times 0.18 square over 2.5, 0.036 kilogram meter square. Okay, 3b. The cylinder is then replaced by a hollow cylinder of the same mass. Discuss qualitatively the effect of the speed of the mass after the mass has fallen through a height of 5 meters. So we want to see what is the changes. Okay, so cylinder is replaced by the hollow cylinder. Moment inertia for cylinder is equal to 1 over 2 mr square. Hollow cylinder is I equals to mr square. The moment inertia of the hollow cylinder is greater than the moment inertia of the cylinder. Okay, since moment inertia of the hollow cylinder is greater than moment inertia of the cylinder, therefore the angular accelerations for hollow cylinder is smaller than angular accelerations for cylinder. So therefore, if you compare torque equals to I alpha, the moment inertia for hollow is greater, meaning that the angular accelerations will be smaller. Therefore, the acceleration of the mass is smaller and the time taken for it to fall through the same distance, it will take a longer time. Questions number 4. Above shows a string wound around the wheel. Okay, so this wheel will rotate downward. Okay, it will rotate downward, and with the free end of the string tied with the cylinder. The mass of the wheel is 0.5 and the radius is 0.4 meter or 40 cm. When the wheel is released, okay, when you release, meaning that initially is U equals to 0, it will fall downward and at the same time it rotates. If the moment inertia of the wheel about its exit is 0.2, calculate the linear accelerations of the wheel and also the tension. So we want to find A and also we want to find T. Okay, so for this case, we have two equations. Okay, the first one is for rotational. So for rotational, torque equals to I alpha, and the second one, the linear motion, is F net equals to ma. For this wheel, it will rotate going downward. Okay, it will going downward, rotating. So it experiences a tension, and this is a radius R. Okay, torque here is R times tension sine 90 degree and is equals to I alpha. Okay, where our tension here is equals to I alpha over R. So we can change alpha equals to A over R. Okay, so our equation will become I a over r squared. This is our first equation. For linear motion, this object is experiencing tension, and at the same time there is a weight acting on this object. Okay, so since the motion is going downward, meaning that is mg minus tension equals to ma. So therefore, tension will equals to mg minus ma. So this is our second equation. Okay, so we substitute equation 1 into equation 2. Ia over r square is equals to mg minus ma. So the first one, we want to find a first. Okay, so we factorize out the a. Ia over r square plus ma is equals to mg. So therefore, a is equals to I over r square plus m equals to mg. Okay, so you substitute into the equation. A is equals to mg, m is equals to 0.5, g is 9.81, then over I is 0.2, r square is equals to here 0.4, so 0.4 square plus m is 0.5. Our acceleration is equals to 2.8 meter per second square. Okay, so after we found a, we can find tension. Okay, so either you use tension equation 1 or equation 2, also you will get the answer. Okay, so for example, let's say I use equation 2. So I substitute T equals to mg, 0.5, g is 9.81, and then I minus the acceleration 2.8. So finally, tension, I will get 3.50 Newton. Question number 5. A wheel of the radius 0.2 meter is mounted on the frictionless, meaning that we can ignore the frictional force. Okay, the moment of inertia of the wheel is 0.05. A light string wrapped around the wheel is attached to 2 kg of the block that slide on the horizontal frictionless surface. A horizontal force of the magnitude P is 3 Newton is applied to the block as shown in the figure. Assume that the string does not slip on the wheel. So first one, we must sketch free body diagram. Okay, so free body diagram, for this object, there's a normal force, and here there's a F external, and we have mg, and also we have tension. And the wheel here is experience a tension. Okay, so sketch a free body diagram. So this is the wheel, and this wheel is experience a tension. Okay, and for this object, there is a normal force, weight F external, and also there is a tension. Okay, so we can form two equations. The first one is for rotational. Okay, the net torque equals to I alpha, where the net torque here is equals to R times the tension. So R times tension sine 90 degree equals to I alpha, and then our tension is equals to I alpha over R. So this is our first equation. For linear motion, F net equals to ma, where our motion is to the right because external force is pulling the object is to the right. So therefore, to the right, our F external minus tension equals to ma. Okay, where our F external here is equals to 3 minus tension equals to m. M is equals to 2 times a acceleration. Okay, so this is the second equation. Okay, so our tension will equals to 3 minus 2a. Substitute equation 1 into equation 2, where we can write as I alpha over R equals to 3 minus 2a. Again, alpha equals to a over R, so we can change I a over R square equals to 3 minus 2a. Okay, so we factorize a, I over R square, a plus 2a equals to 3. So a will equals to 3 over I over R square plus 2. 3, I is equals to 0.05, and the radius is 0.2 square plus 2. So finally, we will get 0.923 meter per second. But the question asks us to find the angular acceleration. Okay, so we substitute into here. angular acceleration equals to linear accelerations over the radius, so it's 0.923 over radius 0.2. So finally we will get angular acceleration 4.92 radian per second square. So that's all for today. Thank you, class. Bye.